Dark matter is one of the main mysteries of modern physics. In recent years, together with its friend in the firm of dark energy, it has been subjected to increasingly loud criticism within the scientific community. Too many claims from the past are now turning out to be untrue after closer scrutiny. It has come to the point where a group of Korean scientists is currently challenging its issuance of the 2011 Nobel Prize in Physics, calling the calculations on which it is based inaccurate. Meanwhile, in the wider public, dark matter has become surrounded by incredible myths and prejudices, which we will dispel in the next couple of minutes in simple language. To understand where the concept of dark matter comes from, it is not necessary to be an astronomer. Just get out of bed and look down. It is well known that at this very moment, our planet is rotating, and people on Earth are therefore moving at a speed of 465 meters per second or 1,674 kilometers per hour. Almost as fast as professional pilots on 16 fighter jets, but unlike them, there are no effects related to moving at such crazy speeds. We don't feel any motion sickness, objects don't fly out of our hands, and oxygen masks aren't stored in everyone's backpack. To paraphrase a famous quote, the answer to this question is as follows: it's not speed that usually kills, but acceleration towards a point in space. The human body doesn't care much about the speed of movement if that speed is stable and not accompanied by jerks, slowdowns, or accelerations. It's the positive or negative acceleration that gives that feeling of movement and can have a devastating effect on health. Speed by itself is not a harmful thing, and the famous series of computer games from a physics point of view should be called not Need for Speed but Need for Acceleration. Now that we've got that out of the way, let's move on to the next point. The overwhelming majority of the world's population, along with the Earth, is moving at a speed of 1,674 kilometers per hour. Our planet rotates in an elliptical orbit, and as we approach the North and South poles, the diameter of the Earth at that latitude becomes smaller. As a result, a person living in the North covers less distance in one full rotation than a person living on the equator. The basic formula for calculating speed divides distance by time. As the distance covered in 24 hours is less at higher latitudes, the resulting speed of people living in France, for example, is lower than that of people living in Ecuador. The maximum speed of rotation of the Earth occurs where its diameter is greatest, that is, on the equator. So people are also moving at a speed of 1,700 kilometers per hour on the equator. Why is this important? Remember how we used to ride on a spinning carousel in the yard as children? Besides feeling dizzy, what did we feel there besides nausea? The physics was trying to throw us to hell from that swing, and the higher the speed, the greater the force. Imagine a carousel in an amusement park that spins people around suddenly stops. What will happen to them? They will be thrown in different directions, not in a circle. This is due to centrifugal and centripetal forces, as well as the Coriolis force, but we promise to explain this in simple terms, so we won't go into them. What is important to us is that the Earth is exactly the same carousel, and those who ride it at the equator move faster. As a result, the laws of physics want to throw them off this carousel harder than those who live farther north and move slower. This is very easy to verify. Stand on a scale at home, then go to the equator and stand on a scale again. If your weight at home is 50 kilograms, then at the equator, it will be around 48-49 kilogram, depending on your initial latitude. There is no magic here. The mass of your body will remain the same. Gravity at the equator is slightly lower, but the centrifugal force is maximum. At different times in our lives, we have all wondered why the rotation of the Earth does not throw us off its surface. Now you know that it does, in fact, throw us off, especially actively at the equator. However, gravity and other forces compensate for this process. Now, keeping these facts in mind, let's move on to dark matter. Just as physicists have studied the process of movement and rotation in spiral galaxies with some qualifications, they have found that stable stars are not thrown beyond their boundaries every day, just like a catapult. This means that their carousel is not broken, and in galaxies, gravity, like on Earth, compensates for all of this. Scientists have verified and calculated this, and there is no doubt about it. They couldn't get the numbers to match, to put it mildly. The discrepancies were not just a few percent, but rather several times over. It's as if you and I reach the size of the moon, but somehow still manage to be held on the surface of the Earth without being in harmony. That's not supposed to be possible. Or, if the Earth were spinning so fast that gravity couldn't hold us, but it does. This is what happens with most galaxies in the night sky. They rotate faster than they should, and the equations of current physics are screaming that at this speed, galaxies should be torn apart like bananas in a blender. But when observed, they behave as if nothing is happening. This raised the question for scientists of how to explain this phenomenon without taking away Nobel Prizes from all the scientists of the 20th century. On stage came dark matter, as physicists calculated the necessary gravitational effect to keep galaxies stable, subtracted from it the number of real gravitation, and voila, here is dark matter. According to these calculations, in the universe, dark matter comprises 27%, while ordinary matter is only 5%. This huge gap negates any possible calculation errors. If dark matter was 0.5%, then one could speculate about inaccuracies. However, when the universe needs 6 times more substance than it actually has for normal functioning, this is already a big deal. It is essential to understand 2 points here. Firstly, dark matter is a pure patch, a crutch in the form of a fictitious substance to make current physics work as it should. There is nothing wrong with it. The boson was also a crutch in its time. Higgs and his recently discovered particle were indeed a theoretical substance called the phlogiston that was used to explain the process of combustion for 200 years before it was realized that phlogiston does not exist. The second and most important point is that dark matter is not actually matter in its original sense. Dark matter is gravity, and many serious scientists like Neil deGrasse Tyson refer to it as dark gravity. By studying the velocities of galaxies, we see not matter, but specifically gravity, which is the only effect of its existence that has been truly proven. In modern physics, it is believed that only matter exerts gravitational forces, hence the name dark matter has stuck. However, if you can prove that something else besides matter can cause similar gravitational effects, then you will earn the Nobel Prize, and this is what the entire scientific community is striving for. The primary goal is to explain the observed gravitational effect, not to find a new type of matter, which is what many people are currently working on. The most popular model today is the so-called modified Newtonian mechanics. It solves the problem of dark matter not by trying to find a new type of matter, but by trying to clarify the laws of physics and explaining that gravity works differently than we thought. As a result, the existence of dark matter becomes unnecessary. On the internet, you will find many videos claiming that modified Newtonian mechanics is outdated, but this is ironically based on outdated data. In May 2022, Japanese scientists demonstrated that theories of dark matter cannot be applied to one of the dwarf galaxies, and their theory works just fine. This brought attention back to modified Newtonian mechanics and other theories that attempt to explain the gravitational phenomenon without the intervention of dark matter. There is an explanation in simple words. The next myth about dark matter is that supposedly we know nothing about it. In fact, we know a lot. For example, it is absolutely certain and with 100% probability known that dark matter does not interact not only with ordinary matter, but also with itself. Ordinary matter, which we are made of, has the property of being influenced by gravity and other forces, causing particles to come together to form more massive objects such as stars, planets, and us. Dark matter, on the other hand, does not form particles. Although we cannot see or detect it, and we cannot sense its presence in any way, if it formed galaxies, we would see how they interact with ours, and we would observe planets suspiciously orbiting around empty spaces. However, such processes are not observed in the universe. This gives another argument to supporters of explaining gravitational effects without using the word matter. To be honest, there is a myth working in their favor. From this video, it may create an impression that dark matter is a fake and physically impossible. However, it is impossible for absolutely indetectable matter, which is also 6 times larger than usual, not to exist in the universe, isn't it? Unfortunately, right now, through your body every second, there may be 100 trillion particles called neutrinos. They are incredibly tiny, but still have mass and pass through everything. Some influence on the more familiar particles in the universe is exerted by neutrinos. Every second, 60 billion neutrinos pass through a patch of land measuring 1 square meter. And these are only the ones emitted by the sun. However, due to their small size and reluctance to participate in most fundamental interactions, even the densest of materials are like a sieve for neutrinos. Stars are completely transparent to them and are passed through as easily as a knife through butter. If a neutrino detector were to be the size of a human, it would take 100,000 years to detect even one neutrino, given that 100 trillion neutrinos pass through the detector every second. IceCube, one of the largest neutrino detectors on Earth, operating at the South Pole, detects only 275 interactions per day, despite having a volume of 1 cubic kilometer, which is sufficient to fill 1 million swimming pools with water. Against this backdrop, it is readily believed that there are even heavier particles that exist, which may well be the elusive dark matter that scientists need to glue the cracks in modern physics with dark energy. By the way, the situation is almost the same. If you want a detailed video on this topic, let us know in the comments. Well, that's all for now, friends. See you next time.
New ideas in science. Deepen your connection to nature, to the stars, and to each other. Learn to see the world differently. we truly see the universe when we open our eyes? Do we see the vast potential that's inside of us? First came fire, then came steel. And it wasn't long before we started asking some big questions. Who am I? Why am I here? Some of the greatest minds in our history, Pythagoras, Socrates, Plato, Rumi, Leonardo da Vinci, Michael Faraday, Max Planck, Nikola Tesla, and Albert Einstein all start to explore the big questions of life and our universe. Their collective work points to something very important, that we might be far more interconnected than anyone had ever thought. Their ideas were way ahead of their time, so they left hidden messages for others to find later, because in their day they could only share their knowledge with a few people. We live in an age where we can communicate to every point on the globe. We are all connected. But it's more than just a feeling. It's also a mathematical equation. But the idea that we are all connected sounds like a platitude to many of us. We're more disconnected than ever in certain ways. War, violence, greed, tragedies. These are the stories that fill the news channels, and this is a very disconnected view of the world. Us against them, you against me, danger and disaster lurking around every corner. But are we complicit in it? Because this is what so many people seem compelled to watch, drawn to the worst aspects of humanity. And then there's the ever-increasing pace. Why do we race through life so quickly, taking in disconnected message fragments with no voice, heart, or context? When we consume bite-sized pieces of information, it's very hard to imagine the big picture. Why does our world seem so frantic? Why do we spend so much of our time chasing money, career, intimacy, and possessions, with schedules so full when all we really want is simply to be together? For all of our progress, we've lost connection to the one thing that really matters. We remain disconnected while pretending to be connected. And being connected at a distance makes it easier for some people to say hurtful things. We have trouble staying connected to the ones we love, let alone the rest of humanity. There is fear and there is beauty. Which world do we want? How we connect with the world changes our experience of the world. There is hidden mathematics that underlies all of creation. Nassim Haramein believes the world is profoundly connected. Our universe is filled with mystery. Our planets, stars, and galaxies account for only 4.9% of the matter of the universe. So what makes up the rest of the universe? Is it dark matter? Is it dark energy? There is a large amount of unexplained energy in our universe. In 1992, the NASA Cosmic Background Explorer detected fluctuations in the background energy of the universe. To explore this mystery, we need to remember the words of Nikola Tesla. If you want to understand the universe, think in terms of energy, frequency, and vibration. There is a flow of the energy of the universe around you and a flow of the energy of the universe inside of you.
When people realize that everything is connected, this sense of separation, this sense that we're isolated, hopefully that goes away. And it's replaced with this feeling that we're part of this incredible creation in which everything is interdependent on everything else. And that everything is connected through this energy that's in the space. And then actually it's the space that creates matter and reality and them. They're part of the whole thing. And so that they can see the incredible potential that they have, the incredible miracle that it is that they're alive and that they're able to experience this interconnectivity with everything. It's a feeling of resonance and a feeling of connection with everything in the natural world. And maybe, just maybe, as a result of understanding this at a deeper level, they will start to understand themselves at a deeper level and understand the functioning of the universe at a deeper level. And that it will give hope to people.
Could there be a scientific basis to the way we are all connected? Albert Einstein changed the world with one equation. Yet he knew that his greatest work, to create a single unified theory of the universe, was never finished. Einstein knew how important it would be to humanity if this could be discovered, and he kept searching for answers. But before he could solve it, he ran out of time. Others have built on the work of Albert Einstein in the search for a unified theory of everything. Some people have a knowingness of this connection between the macro and the micro. In the past, we've created mythology around it. But what if we could understand it through the lens of science? Nassim Haramein has been exploring how everything is contained in everything else. The exploration of the universe through mathematics and physics has been complex. Yet from this complexity emerges simplicity. What if there is a way of proving that everything is connected and one at the same time? To understand this, we must take a journey, and our journey begins with the proton. If you remember back to your high school science class, atoms are everywhere and the protons are at the center of every atom. Therefore, we must accurately understand the proton if we're going to understand the universe. New measurements of the proton suggest we must change our existing way of thinking. Nassim Haramein was the first person to have accurately predicted the new measurement of the charge radius of the proton. The proton could hold the key to a scientific understanding of how the connection of the universe actually works. 1905. Einstein demonstrated through an example of a person traveling on a train the theory of relativity. He unified the separate camps of energy and mass with his famous formula. But later, a great divide in physics occurred when Niels Bohr and a group of physicists split off to explore quantum mechanics. They saw two worlds, a quantum world that describes the probabilities and the uncertainties of the very small, and the separate mathematics for the larger universe. Creating this division led to a very disconnected way of thinking. Nassim Haramein, the Director of Research for the Resonance Science Foundation, has been on a lifelong search to discover a unified theory of everything.
My passion for learning never subsided. As soon as I left school, I got more passionate than ever about understanding the universe, studying physics and mathematics and so on, to try to describe it better and eventually to write a unified view of physics. To me, it was critical that we understood the source of reality. We come here and we experience this life, and most people don't ask, like, how did I get here? What is this life? How am I moving billions and trillions of atoms around? I was exploring all this for my own personal satisfaction. It really wasn't to get a master's degrees or a PhD in some institution. I knew that if I went to the institution, I felt I was going to be restricted. I knew I was going to be given very specific concept that I would have to go with. I didn't want that. I wanted to be completely free to think what I wanted to think as I explored. It led me down a very specific road. Certainly some of the things I thought turned out to be wrong, but eventually I started to home in on the stuff that worked together, and I found something, I think, very fundamental and very profound.
To understand how everything is unified, Nassim had to study nature. He had to look at patterns. He looked at the macro and the micro. He started asking questions about some of the fundamental principles science has taken for granted, and started to wonder if, somewhere, we went off on the wrong track. As he continued his journey, he began to understand that in order to see how everything is connected, we had to look at everything.
Everything we experience as reality is actually made up of 99.99999% space. The little part that's not space, or the little part we define as something, the material world, is actually just a little oscillation, a little electromagnetic boundary that we are bumping against, and we call that our reality. We call that a stone, an atom, we call that the water, the sand, or a star, a galaxy. And so maybe instead of looking at matter, defining the space, I start to think maybe it's space that defines matter.
It is fascinating to realize that if you remove the empty space in every atom of every human being on the planet and compress it all together, all of humanity would fit into the size of a sugar cube. Granted, it would have the density of a neutron star and weigh approximately 478 million tons, but this helps us to visualize the importance of understanding that every one of us are made of mostly empty space. But as it turns out, that space is not empty.
It was found that space-time at the quantum level is fluctuating with intense energy level, full of dynamic energy components.
We are not only talking about the space outside of our planet. We are talking about the space inside each and every atom of your body. Every single human on this planet has this in common. Regardless of race, color, or religion, we are all individual beings, yet this dynamic energy of the universe is constantly flowing through all of the space inside each one of our atoms, connecting us all. This helps us understand the profound quote of the Sufi poet Rumi, who said, "You are not a drop of water in the ocean, you are the entire ocean in a drop." You can literally feel the force of the universe inside you and flowing through you, connecting you to everything, because you are a part of everything through this dynamic energy. The great theoretical physicist John Archibald Wheeler, a colleague of Einstein, said, "No point is more central than this, that empty space is not empty. It is the seat of the most violent physics." The theoretical physicist David Bohm explained, "Space is not empty. The universe is not separate from this cosmic sea of energy." And Albert Einstein said, "Physical objects are not in space, but these objects are spatially extended as fields. In this way, the concept of empty space loses its meaning." This underlying background energy that exists everywhere in space is described in physics as the vacuum. What if there was a way to connect to this vacuum energy rather than depleting our natural resources? Humanity is on a course that's unsustainable.
For millions of years, magnetic fields have been around us without us knowing about them, until Faraday figured out that by moving a little magnet across a set of wires, we could get an electric power source that could power all of the devices we use today in our society. Now we are discovering there is another invisible field at the source of the material world that is all around us and in large quantities. And by learning how to tap into its structure, we could power our world for generations to come.
Scientists from around the world are looking for a solution to tap the vacuum energy that is all around us. And it is important that they succeed. Current wars and potential conflicts of the future will be fought over resources, like oil and water. Abundant energy will help create stability in the world and reduce the threats of the perceived energy supply disruptions that cause countries to go to war. War has been a big part of humanity's past. But does it need to be a big part of humanity's future? War has brought untold sorrow and suffering to mankind, and it is perhaps the strongest example of what can happen when we become so disconnected. Gandhi said, "An eye for an eye makes the whole world blind." With our modern capacity to wage war, there can be no victors. Gene Roddenberry, the creator of Star Trek, once said, "The strength of a civilization is not measured by its ability to fight wars, but rather by its ability to prevent them." Learning how to harness this vacuum energy all around us could have profound implications, but it will require a paradigm shift. Some of the greatest advances in science have come from people with the courage to pursue ideas that challenged the accepted wisdom of the time. It was common for these new ideas to meet with rejection at first. Galileo was imprisoned. People resisted Faraday because he had limited formal education. And do you know what happened when Einstein published his great works in 1905? Nothing happened. People didn't connect to his ideas. The only person who really saw what Einstein had done was Max Planck, who would become the father of quantum theory.
Pursuing an independent path outside the academic world has been extremely difficult. It has been painful in many circumstances. The feeling of continuously being rejected, of not being understood, the constant interaction of fighting preconceived ideas has been a long road. However, it has forced me to be more accurate, to continue digging deeper, and to be extremely careful about my calculations and how I bring them into the world. So it has served a certain purpose.
Our material world is not as solid as it appears at the quantum level. As Tesla put forth nearly a century ago, we need to think of the universe as energy, frequency, and vibration, not as solid physical forms.
We're not dealing with little billiard balls. We're dealing with waveforms, oscillations in the vacuum. Just like when we throw rocks into a pond and the rings come out, the rings can intersect and it doesn't destroy the waveform of one of the rings or the other. The two just intersect. And so that the spheres, the little vibrations of the vacuum are intersecting, and it is the holographic structure of space-time itself. It is the interference pattern that encodes the information of the whole universe in every point.
The idea of a holographic universe was first put forward by physicist David Bohm, advanced by Gerard 't Hooft, then later expanded by Leonard Susskind. It was inspired by new understandings of black hole thermodynamics, that the information of the black hole is present on the 2D surface of the black hole, known as its event horizon. A simple example is that if you throw a wallet into a black hole, as the wallet is being consumed by the black hole, all the information contained in the wallet would become present on the surface of the black hole, because it is a rule of the universe that matter cannot be created or destroyed. Holograms are created using lasers to capture and encode the information of an object in the form of an interference pattern. The light reflected from the object is combined with that of a reference beam to create an interference pattern which can be retained on a photosensitive surface, creating a complete image that can be viewed in its entirety from all angles. The information of the whole is present at every point. When the hologram is cut in half, the complete image is present on both pieces. When it is cut again and again, every piece still contains the representation of the whole image. It is not the actual object, but a representation of the actual object in every piece. Nassim Haramein believes that the representation of the universe is encoded by the interference pattern of the fluctuation of space-time on the surface of every proton. The difference from the static hologram example is that the holographic information encoding is dynamically happening at every microsecond at every moment, and it is constantly flowing throughout the universe.
We often hear the sentence or the concept, everything is connected, it's all one. We hear that from even masters in ancient civilization or modern thinkers, philosophers, spiritual people. And it's a great concept. For many people, it resonates as something true, but how is that true? Some of the work I've been doing starts to open the door to understanding the dynamics and the mechanics on how everything is connected, so that it's no longer just a dogma or an idea, but it's actually based on the physics of reality. When I look carefully at the natural world, I found high level of coherency, high level of geometry, and as well this interconnectivity, this interdependency of all things with other things. The whole system functions together in a balanced way. And I started to wonder, what is the source of this self-organizing system?
What do you see? It depends on how you look. You could scan around an object and study it. Then you could look more closely using a microscope to isolate each part. In this instance, you would see millions of fibers and could spend a long time studying them. When you look too closely, you only see part of the picture. It is when you pull back that you see the part each fiber plays and how it is related to the others, and then the bigger pattern emerges. Imagine the new understandings we will gain if we could all learn to think differently and to look at our world through a big picture, connected perspective. Einstein believed that geometry was a key in the search to understanding the unity of the universe because it represents the relationship between things. Great thinkers came to discover the underlying geometry of nature, such as the golden ratio and the Fibonacci sequence, in many different forms of life. When Nassim Haramein analyzed these geometric relationships in a changing three-dimensional space over time, he saw the 1 to 1.618 ratio appearing, known as the golden ratio, or phi ratio, as a fundamental part of the structure of space-time. Leonardo da Vinci encoded this in his famous work, The Vitruvian Man, showing that the phi ratio exists in different proportions throughout our bodies, and it's not just in humans. It is in animals, in plants, and in art. Geometric symmetry even affects our perception of beauty.
Spending time in nature teaches us that everything is interconnected and everything is interdependent on each other. We have a tendency to isolate systems and then analyze them as if they were not in relationship with anything else in the universe, so that many of our laws of physics starts with the statement within an isolated system. But then if you look up isolated system in a physics dictionary, you find that no such thing has ever been found. That is, nothing can be isolated completely from everything else in the universe. Gravitational fields cannot be isolated, electromagnetic fields, and so on. So we need to write science that takes account of the relationship of all things with each other. I think if we want to find the fundamental principles of creation, we have to experience nature from an experiential base. And then the mathematics should come together simply and show beautiful results. It's too easy for scientists to get into the laboratory and just keep trying to work out the theory and lose contact with the natural world. When I'm out there surfing, I'm actually constantly being connected to these fundamental patterns of nature. The particles going up and down in the wave, the energy wave pushing me through the ocean, getting inside a barrel, the big vortex, and the dynamics of the vortex. There is something very profound about that. Many of these things inspire me when I go back in the laboratory and start writing formulas. It's like it's in my cellular memory then.
For many of us in cities, nature is but a faint memory. We are overrun by our technology. We give such importance to our digital reality that we sometimes ignore our physical reality at great peril. And it takes up so much bandwidth, affecting our performance and our well-being. We've let the noise of technology drown out our inner voice, which Nassim believes is the source of inspiration. We need to occasionally disconnect in order to reconnect.
Some of the most beautiful times of my life were times where I was extremely isolated. So at that time, I was coming up to Whistler, Canada. More and more the interest I had in nature and physics and understanding the basis of reality was kind of taking over my interest. So I moved into a van to continue my research. I knew that if I could tough it out, minimize my expenses, I could get enough resources so that I could continue to work full-time, doing research, trying to find some clues as to how I could unify the forces of physics. And I was in this amazing research zone where information was just flowing through, and I was researching, I was finding more and more information, and the pieces of the puzzles were coming together, and moments after moments of illumination. Oh my God, oh my God, oh my God, one after the other, and it was just so beautiful. It was the most transformative experiences of my life. And most of the physics I wrote here. Of course, it took me some 25 years to flush out the math for it, but I knew I was onto something very early on. I was learning advanced physics, and I was coming to very specific conclusions, and then I was decoding ancient texts and ancient traditions that were completely confirming what I was coming up with in advanced physics and how the world comes to be and how the material structure exists. And many of these civilizations where these ancient symbols were present had numerous, thousands of different, very strange anomalies. Some of the things that are found around the world are not even reproducible with all the technology we have today. I felt that in these symbols, in these secret geometry, that these pointed to very fundamental understanding of the structure of space, of how matter is created, and how gravitational field can be controlled. It was my intent that the theoretical studies I was making would eventually lead to advanced technologies that would allow us to control gravitational field and electromagnetic field in such a way that it could transform our civilization.
Many in the Western world misunderstood the teachings of the Mayan culture and thought December 21st, 2012 was going to be the end of the world. However, the Mayan elders have said directly December 21st, 2012 wasn't the end of the world. It was just the end of the old cycle. Now we have the chance for a new beginning, a new era of connection, new understanding, and interestingly, on that day, December 21st, the end of the Mayan calendar, Nassim Haramein sent his paper to the Library of Congress, which for the first time ever connected quantum and cosmological physics.
And the result of my equation was the exact gravitational mass of the black hole. That is, if I solve Einstein field equation to figure out the mass of a black hole, I would get the exact same result. So all of a sudden, I knew from the beginning of this exploration that I found something profound. If space is what's connecting everything, if space is what everything emerged from and returned to, then space is the great organizer. Space is the thing that connects all things, that gathers the information of all knowledge of every point in space. If we look at all the little fluctuations of the vacuum, the amount of energy inside a proton, in the vacuum fluctuation, the mass of the vacuum inside a little teeny proton in the center of an atom is equivalent to all the other protons' mass in the universe. That is, all the rest of the matter in the universe is represented holographically by the vacuum fluctuation inside one little proton, so that one little proton is connected to all other protons in the universe.
Nassim's calculations seem to present evidence that our universe is holographic in nature. Another big question in our effort to understand the nature of things: is the universe random? Think of the amazing biodiversity of our planet, of all the living things. We live in a wondrous world. Think of the complexity of a chimpanzee. Consider a jellyfish, or a blade of grass, or something less complex, something not alive, a simple Rubik's Cube. 3 rows, 3 columns, 3 deep, with 6 colors. What is the mathematical probability of solving that by random chance? 13.8 billion years is the current estimate of the age of the universe. If you could send a blind person back in time with a scrambled Rubik's Cube, and they could make one move every second, how long do you think it would take them to solve it? In the 13.8 billion years of the existence of our universe, you would have less than a 1% chance of solving it. So how much longer would it take to ensure that you would solve it? There are 43 quintillion possible states for the Rubik's Cube. To move through every possible state without ever repeating the same one, it would take 1.4 trillion years. And you would have possibly solved it at some point. But it could have taken billions and billions of years longer than the existence of our universe to solve a simple Rubik's Cube by random chance. Now imagine the incredible complexity of a human being with 100 trillion cells that are communicating every millisecond to ensure all systems are go. Imagine all the moving parts, all the possibilities. How long would it take to organize that? Because we are so vastly more complex than a Rubik's Cube. Yet humanity exists. So how can this be possible? What if we could tell the blind person something?
If we give just one little piece of information, yes, you're going towards the solution, or no, you're going away from the solution, then within a few minutes, the Rubik's Cube would be ordered. So from billions and billions of years to a few minutes with one simple feedback of information, that gives us a clue about the probabilities of how the biodiversity and the structure of cellular systems and all of our complexity that occur could have come to be with one simple feedback in the structure of space itself.
Our universe cannot be purely random. There must be a feedback mechanism in the flow of the universe. Further evidence that this must be happening can be seen in fractal mathematics. For thousands of years, traditional mathematics mostly described man-made objects and motion. It could describe a pyramid or a column, but for living objects like a flower or a tree, you need fractal mathematics. Fractal mathematics are the underlying patterns that build the natural world. The great mathematician Benoit Mandelbrot created computer programs that use fractal mathematics to render complex forms. When Hollywood wants to create a whole new world in a science fiction film, a new planet, new plants, and new life forms, they use animation based on fractal mathematics to create a complexity of the natural world. To describe nature using math, you also need a feedback loop called iterations. If you start with a simple form, then iterate the formula, which means the formula feeds back on itself. You can see the complexity grow with each iteration. It is fascinating and beautiful to watch. When you make tiny adjustments to the formula or to the base form, you can create vastly different results. The possibilities seem virtually limitless. Witnessing this incredible variety and complexity helps to understand the vital role that the feedback mechanism plays in our universe.
What is consciousness? What is the experience of being self-aware? In order for such thing to occur, there must be a feedback of information. For instance, you looking at yourself in the mirror, knowing it's you. What if consciousness is actually a function of how space feedbacks on itself, which would be a dynamic that could generate self-awareness? Us feeding information to the structure of space-time, and space-time feeding information back in terms of our experience every day. This feedback mechanism could be the source of the self-organizing system that we see all around us at the biological level, and eventually becoming self-aware or conscious. This being the very extension of space-time looking back at itself and learning about itself.
Starting out in the world, when we first gain consciousness, we learn to take in information from all around us, from parents, from books, and now from technology. We are living in a time of information overload, and we are being bombarded by messages from everywhere. We have almost infinite choices in what messages we consume. It matters a great deal what you focus on. We know the universe has a feedback loop, and our brains have a feedback loop as well. Our thoughts are not only imprinted on the universe, they also deeply affect how we experience the world. The gift of being conscious is the ability to feel the wonderful moments of life. And it also means that we feel the painful moments. As you get older, you realize that good times don't last forever, and neither do the bad times. Because our brains have a remarkable ability to adapt. We can learn to shift our focus, to change our experience by changing what we put into our feedback loop. Gratitude and positive thoughts can build on each other, creating an upward spiral by connecting to your friends and to nature. You have the power of the universe inside of you, and you can overcome anything in life. Remember the age-old words, this too shall pass. As an individual, you put your thoughts and intentions out into the universe. And through the feedback mechanism of the universe, the collective energy of everything flows back into you. You are in a constant cosmic dance with the universe. The great poet Rumi said, "Stop being so small. You are the universe in ecstatic motion." As individuals, we are powerful, but we have even greater power when we dance together, when we collectively focus our energy, when we share and focus the flow. The flow of energy is real and we can feel it. Some people have learned to connect in their inner journey through yoga and through meditation. Some people's only experience of this is cheering at a major sporting event with tens of thousands of other fans, cheering for a common goal, which is enjoyable, but it is capable of being so much more. Humanity is able to accomplish amazing things if we come together on a global scale to create positive change and elevate our collective evolution. You matter in the universe. You are part of the cosmic flow.
I think that every person is an incredible miracle, and every person is critical to our evolution.
Your body is an incredible example of interconnection and synergy. All the systems working together without even a conscious thought, in concert with your brain. Your brain may be one of the most amazing things we know about in the universe. It's doing billions of operations per second and doing everything it can to keep you alive. If you take a moment to connect to your body and appreciate all the invisible processes it does for you, it heals your cuts, helps fight disease, gives you energy. What if you stop being judgmental about the appearance of your body and choose to love your body for the incredible miracle that it is? How do you think your life will change? Your body is the vessel by which you experience the world and the universe, and it allows you to be part of the cosmic flow.
If people understood the miracle that they are, they would never be down on themselves. They would never feel like they are, less of. They would realize that they are part of an incredible will work of nature that they have access to, and that they have power in this universe. They can do things, they can transform things, they can transform themselves, and as a result, transform the universe.
famous mathematician Benoit Mandelbrot proved that the smaller the unit of measurement that you use, the more accurate your final result. This is important to the work of Nassim Haramein because he uses the Planck units, the smallest unit of measurement available in the universe, in his calculations, which leads to an unprecedented level of accuracy. So, how incredibly small is the Planck unit?
In order to give you a conceptual notion of the relationship in size between the Planck and the proton size, if the Planck was a little grain of sand, then the proton would be the size of the distance between the Earth and Alpha Centaurus, an enormous bubble that spans large amount of space, some 4 light years across.
And then fill it with grains of sand. That's how many Planck units are in the proton. Imagine every grain of sand on the Earth would just be the tiniest speck of the number of Planck units on a proton. Not only does this show how small the Planck unit is, but it also shows how many Planck units fit in a proton. Haramein calculated that all the little Planck pixels add up to all the information of all the other protons in the universe, and that the fluctuation of the Planck oscillators creates the information network that the universe uses to get constant feedback. Einstein was fascinated with light and how it worked. His famous thought experiments would lead to several counterintuitive ideas that would forever change our world. One of those ideas was his theory of relativity. Einstein's general theory of relativity explained gravity as a consequence of the curvature of space-time created by the presence of mass and energy, and that space-time could be calculated through geometry. It literally acts like a fabric that stretches and bends. When you put lighter objects near a heavier one, they spin in the gravity well created by the large object. Einstein saw the fabric of space-time and gravity as continuous. Haramein sees the fabric quantized with a sea of almost infinitely small Planck pixels. So it behaves like Einstein's fabric on a cosmological scale, but the big breakthrough is that because it is made of tiny quantized Planck pixels, it allows for the forces of spin and gravity to be accounted for by Haramein's geometry at the quantum level. If you think of the water in a perfectly still kitchen sink, it could look like a single sheet of water. But if you pull the drain, the water spins around the drain while the rest of the surface is perfectly flat. This is how Haramein's work gets results like Einstein's single sheet. Yet because the water is really tiny individual drops, it allows for spin to be present at the quantum level. The other difference is that we can't think of it as a single sheet. Think instead of it being stacked infinitely high and infinitely low, infinitely right and infinitely left, in a giant Planck pixel soup that fills the universe, allowing spin to occur anywhere.
Einstein geometrized space-time at the cosmological level, and until he died, he believed that there were gonna be a solution to do the same at the quantum level. So I was very much inspired by that.
As Einstein was fascinated by light, Haramein is relentlessly fascinated by the forces of spin.
Everything in the universe has spin. And I came to conclude eventually that the fundamental torque that produces the spin comes directly out of changes in density in the structure of space itself. Just like a little change in density between hot air and cold air produces a hurricane, which, if you look carefully, looks a lot like a galaxy. The same forces are generated in the structure of space itself because of a gradient or a change in the density of the energy of space. The structure of spin is critical to our understanding of the dynamics of the universe.
Think about all the ways we are spinning. The Earth spins at about 1,000 miles per hour at the equator. The Earth spins around the Sun at about 67,000 miles per hour. The Sun, with our solar system, is spinning around the galaxy at 515,000 miles per hour. The galaxy is moving through the universe at approximately 1.3 million miles per hour. Our DNA expresses spin. Atoms spin, protons spin, everything in the universe spins. Spin may be the one thing that connects us all. We are living in a universe where everything inside of it spins. Seeing the interconnection of all spinning things made Haramain look at gravity in a different way. Gravity is one of the most mysterious forces in the cosmos, which is why so few quantum models include gravity. This is part of the reason for the disconnect between the quantum world and the cosmological world. Haramain asked the question, where is the best place in the universe to observe the most intense interaction of the forces of spin and the force of gravity? The answer? The edge of a black hole. Haramain has studied the possible connection between the forces of spin and the forces of gravity being intertwined at a quantum level.
The spin dynamics of the structure of space-time itself is what produces what we call the black hole. And this new equation proves that. It proves that it's the Planck fluctuations that produces the effect. The black hole is actually the result of the little Planck's vacuum oscillations dynamically, collectively organizing.
From this new perspective, we start to see galaxies in a new way. Haramain's theory predicts that there may be a supermassive black hole at the center of every galaxy.
It'll be almost like spinning a coffee in the morning, where the coffee is completely black, a very dark black coffee, and you can't actually see the spin very well. But as soon as you put the cream in the coffee, all of a sudden the spin appears. Like the stars and the dust and the electromagnetic radiation in a galaxy makes the spin that's already present in the vacuum apparent to us. And we go, oh, look, there's a galaxy with a black hole in the middle, where the black hole and the structure, the spinning galaxy, are actually present prior to us being able to see it. Universal black holes, these huge giants in the middle of galaxies and quasars and so on, are actually the same dynamics inside a teeny object we call an atom. And that when we're looking at a proton or the nucleus of an atom, we're looking at the same structure, the same dynamics of black hole, but in a very teeny object.
Leonard Susskind, the director of the Stanford Institute for Theoretical Physics, who is best known for having won the black hole war with Stephen Hawking on the information paradox, stated in a mini-lecture series that there is no sharp separation between particles and black holes. Many physicists, including Leonard Susskind, are independently exploring new understandings of black holes. Haramain's proposed connection between the black hole forces and protons could prove highly significant.
We're made out of these objects. We're made out of protons and atoms and molecules and all this. And so it would stand to reason that the same kind of dynamics should be found even at the biological level. And that is what creation is. It actually emerges from the vacuum through the black hole structure into our reality.
New studies have shown that the spin rate near the surface of black holes seems to be very high. They spin close to the speed of light. His theories from 20 years ago predicted that result.
These are all components that tells us that the black holes are not the result of the material world, but maybe that the material world is the result of the dynamics of black holes.
Information and energy flow throughout the universe. For many people, the science of the interconnection of the protons is exciting because it resonates with the feeling of the connection of life. We feel the connection of life very deeply with our loved ones, our families, our pets, with the animals, with the amazing flow of nature and our connection to the natural world. Since our earliest beginnings, humanity has depended on the sun and the stars for food and navigation. The drive to understand the forces of nature at work in our world has pushed humanity ever forward. For millennia, humans have looked at birds and dreamed of flying. But for most of human history, flight was considered impossible. What is the next great advance in flight?
The structure of space-time is all around us. Imagine if we can learn to influence these structures so that we can control them and make them work for us. Gravity is a result of these little fluctuations in the structure of the vacuum. And by controlling those, by influencing those, we could be able to levitate things. Some incredible possibilities open as soon as we understand these fundamental mechanics of gravity and learn to control them and influence them. There's over 50,000 flights a day. Imagine if all these flights didn't require fossil fuels. Imagine the positive environmental impact this would have on our society. However, in order for us to evolve to a society that's able to fly maybe through its solar system or even through its galaxy, our technology, our understanding of the forces of nature, such as gravity, have to go to a deeper level. The helicopters behind me produce massive amount of lift by creating these small pressure differential and generating vortices in the structure of the air. Now imagine what we could do if we could create the same type of depression or the same type of gradient change in the structure of the fluctuations of the vacuum itself. The space would curve and generate what Einstein described as gravity in space-time curvature. By doing so, we could control the gravitational field. Is it possible to create a gradient in the structure of the vacuum itself? We already do this with the Casimir effect, where we create a little gradient between the two plates that forces the plates to get pushed together. And now we've succeeded in doing what's called the dynamical Casimir effect, where actually instead of using plates, we're using little semiconductor mirrors, and we're able to oscillate them really fast, and as a result, we're able to like pop little photons right out of the vacuum. So we're actually already extracting little bit of energy directly out of the vacuum. This opens incredible possibilities. Tapping into the network of the structure of space leads to space travel across very large distances, and so on.
We have already sent probes past Pluto and out of our solar system, and Hubble has peered into the unimaginably vast reaches of space. And we have come to realize that we are connected to it all. Your connection with the universe began long before you were born. Did you know that the atoms and elements of your body were forged in the hearts of stars? Carbon, nitrogen, iron, and then when that star exploded, they were spread throughout the universe. The atoms in your foot may come from a different star than the atoms in your hand, and different from the ones in your heart. We are connected to the stars in a profound way, literally made of stardust. Individual examples of a living, connected universe. Our mountains have watched humanity rise. Yet, what have we risen to? Are we at our best? Are we capable of so much more? Imagine if we open our eyes to new ideas, the heights to which we could rise, and make that journey for ourselves and for all of humanity. Because we are all one. It has been a long road to get to the place where we truly understand the concept, as above, so below, as within, so without. And that the forces of black holes are present in something as small as a proton. This changes the way we see the unity of our world. As the dreams of our future take flight, this becomes an equation for a more connected humanity. Einstein believed that a unified equation should be beautiful in its simplicity, containing no free parameters. This is Nassim Haramein's equation. It contains no free parameters, and it solves for mass and gravity, both at the cosmological and quantum scale, with simple geometry and algebra.
I took the radius, I calculated the surface, I calculated the volume, and then I divided by the little Planck spheres to figure out how many is inside and how many is outside. So that the outside was denoted as eta in our paper and the inside as capital R. And then I just did R over eta. I just looked at the relationship of the inside information to the surface horizon information. And I got a ratio. And eventually, I multiplied that ratio by a mass, the Planck mass. And the result of my equation was the exact gravitational mass of the black hole, just by basically pixelating the inside and the outside of the black hole and looking at their relationship. So all of a sudden, I was getting a solution to gravity, the solution to Einstein field equation, a solution that is based on holography, but not only that, a solution that's based on little Planck pixel. So that it was quantized.
Einstein said we can't solve problems by using the same kind of thinking we used when we created them. Creating this bridge to unify the great divide in physics is an important step forward in advancing a more connected view of physics.
So in the paper that I wrote and I sent to the Library of Congress for copywriting in December 2012, I make this little prediction that the radius of the proton should be exactly this value. And I state in the paper that more precise measurement in the future may confirm this theoretical result. I started to work on getting the paper published and sending it to colleagues around the world. I was getting very good reviews on it from very advanced physicists. And then all of a sudden, a paper was published.
On January 25th, 2013, a new muonic measurement of the charge radius of the proton confirmed Haramain's predicted value. The experimental results were not what the quantum world wanted to hear.
The measurement came in at 4% smaller than what was expected by the standard model. And so it was very difficult for the scientific community to accept this measurement.
Nassim, you're on Yahoo Finance News. What do you think about that?
Oh my God.
CBS.news.
Changing the paradigm as we talk. History in the making.
New connected universe theory offers an alternative explanation of gravity and mass, revealing potential new source of energy. That's big. Look, it's in the middle of the day. I mean, the night.
Oh, that's fantastic.
That's really awesome.
Oh my God, it's incredible. The wire went out, and within minutes it was picked up by some of the largest networks and media on the planet. And it's already across the world. India, Germany, Europe is coming online. The East Coast will in the next few hours, I'm sure. I just feel like, okay, we're making a significant difference now. We're really kind of birthing a new paradigm, a new moment in the history of science and the history of understanding of the universe on the planet. Some 30 years I've been visualizing this moment where my work would appear on major news feeds all around the world.
I mean, we got a lot of pickup on this news release.
Today's the day. And it's kind of strange. It's a strange feeling. It's like, oh my God, it actually happened. And, you know, it seems like a day like any other day. But this is the day that it happened. And this could very well be the day that science changed forever.
But so far, it hasn't been the day that science changed forever. Looking back through history and physics, this is a pattern that has been repeated time after time after time. Someone comes up with an idea that later will become standard, but at the time, nothing happens. And sometimes there is massive criticism about the idea because it's a different way of thinking. We are only now discovering some of the unpublished works of Sir Isaac Newton. He didn't share all of his work because it went against the religious dogmas of his time. It's a little bit like steering a large ship. The wheel gets turned, but there's no immediate change of direction. In the world of physics, it can take years. After he first published his paper, Haramain was invited to share his knowledge with one of the largest laboratories in the world. However, when the administration found out about it, that invitation was cancelled because they were focused on looking for a solution in a different way. after 30 years of work, believing that this would be his moment, history is again being repeated, that potentially a big leap forward in our understanding is not being recognized.
What I'm most afraid of is that the world will misinterpret what I say, misinterpret who I am, and continue on their self-destructive path they are on today. And that this incredible opportunity in our civilization we've had to grow and to evolve to a galactic community will be missed. I hope to be able to inspire people to think differently, to not be afraid to be who they are, and not to take everything they've taught in the school or in the media or anywhere else just as a given, but actually to question what is being said and the validity of it, and to do it in a way that is constructive and that leads to higher understanding and higher levels of creativity. And I hope that my path and all this exploration I've done can inspire people.
Science doesn't always change overnight. The Greeks theorized about the existence of atoms 2,000 years before we could actually detect one. The cover of Scientific American states in huge bold letters, "The proton problem. Could scientists be seeing signs of a whole new realm of physics?" For physicists, the measurement of the charge radius of the proton is fundamentally important to the understanding of our universe. When the first measurement came out in 2010, it was significantly different than the standard scientific thinking of the day allowed. They said there must be a mistake, that there must have been an error. So when a new measurement was done using heavier muonic particles which would allow for even greater accuracy, the results were even more shocking.
And so immediately I purchased the paper confirming the correct radius for the proton and that no errors were found in the earlier experiments. And so I took that number, I plugged it into my equation, and it outputted something remarkable. I was so excited to find that now my prediction is within one standard deviation of their data. And so evidence is supporting that actually our theoretical result might be the exact radius of the proton, and experiments are slowly creeping towards it, confirming the theory very strongly.
Standard thinking says that there are 4 fundamental forces in the universe: gravity, electromagnetism, the strong force, and the weak force. But the strong force and the weak force were theorized before we understood about black holes.
From my study of black holes and scaling laws of black hole structures in the universe, I found that the proton, or the nucleus of an atom, could act as a mini black hole.
If you describe the little proton as a black hole, all of a sudden you calculate the gravitational force of 2 of these little black holes attracting each other, you get the exact force that we call the strong force that holds the nuclei together. Exactly. Not like approximately, but exactly. The strong force, that force that we actually invented out of nowhere because we didn't know how the protons held together, because they're positively charged, right? They're supposed to repel. So when we discovered that, we invented a force to force them to be together. And we said gravity is too weak to do the job. So we invented a new force. And since then, we can't get gravity and the strong force to like be nice to each other. And that's because we invented one of them.
Since then, we've ran like supercomputers night and day, billions of dollars of investment in supercomputing power to try to find an analytical solution to the strong force, to LQCD. Zero solution has been found to this day. So maybe it's wrong, bro. Try that.
Because these little protons are spinning very rapidly, when we move them away from each other, this very strong attractive force drops off very rapidly, which is what we call the Yukawa potential.
Out of the geometry emerge an exact solution to the force necessary to keep the protons together. And out of that came out the spin of the protons. And from the spin, I'd extrapolated the range of the gravitational force of protons to one another.
If they were mini black holes, that force would be completely eliminated. We wouldn't need the strong force because we would realize that it's actually the gravitational force acting at the quantum level. So I am able now to account for the strong force with a gravitational force and eliminate some of the largest complexities in quantum theory and reduce the number of fundamental forces in the universe.
What really keeps me going, this amazing transformation I can see when a person realizes that they're connected to everything and that they matter in the universe. We live an imprint as we go in our daily life in the structure of space-time itself, that we're informing the structure of the vacuum, and so that nothing would be the same if we weren't there. We're actually participating in this incredible, complex will works of nature, and that the communication of all the things in it is occurring through this imprint that we leave on the structure of space-time as we go along, as we interpret what we see and how we feel. And so we have a responsibility in our interpretation and our feelings and our behaviors in what we are feeding the universe.
So what do you want your imprint to be? You have the power in every moment of every day to choose how you feel and to choose how you show up in the world. Your choices matter in your own life and the lives you affect all around you. We can look at the world through the eyes of a child again, be filled with wonder, imagine, create, explore, and question. Our heart is how we feel all the things we can't see. And when we integrate the power of imagination with the love and strength of our heart, our world will change, bringing hope for a better future. And this requires action. We already know about the feedback loop of the universe that creates reality. But there is also a powerful global technological feedback loop in the form of the internet. We consume content, but we also contribute content. Status updates, pictures, tweets, blogs, and we like, we react, we comment, and we share. This is a perfect example of a feedback loop. We live in an age where we can help each other solve problems like never before. One person has a problem, solves it, posts it, and we can all benefit from it with a few clicks on the web. Scientists from around the world can collaborate remotely and give each other feedback like never before. We are living in the most technologically connected time in history. So what are we going to do with this opportunity? Technology is a double-edged sword, and it can cut both ways. Many people think technology alone holds the key to creating a better future for humanity. But there is more to it than that. It is the consciousness with which we create and wield that technology that will significantly impact our world. And the choice is ours. We can choose to do more than just use technology to understand the mechanics of the heart. We can choose to listen to our heart, to connect to it, to be inspired by it, to learn to follow it, and to learn to use it to the fullest. Our heart is part of our grand connection to the universe. Together, we have the power to raise consciousness globally. We can make kindness go viral. We can actively contribute to creating a world where we focus on the good. We can renew hope, create solutions, and we can share old wisdom and new ideas. It would be hard to explain to someone 40 years ago the incredible impact of the simple connectivity of the internet and how it changed nearly every aspect of our lives. It is hard for a young person today to imagine how the world used to be, because everything is changing so fast. Can you imagine what the future will be like in 20 years? Where will science take us? What will our technology look like? What will we learn when we stand inside a virtual reality proton and observe and interact with 3D visualizations of real-time experimental data?
It's really exciting to see the interest that this new theoretical understanding is bringing. We're collaborating with industry and have now state-of-the-art laboratories to produce technological advancements that are critical for the evolution of our planetary system and our society, including energy production, gravitational control, and all these things. So a lot of incredible things are happening, and we're making great strides in achieving a whole new level of understanding of our universe, ourself in it, and a whole new level of technology to go along with it.
It is estimated that human knowledge took 1,500 years to double for the first time. Then by 1900, it doubled every 100 years. By the 1940s, it doubled every 25 years. And in 2013, it is estimated that it doubled every 13 months. And that time span continues to get shorter. But knowledge alone isn't wisdom. Leonardo da Vinci said, "Learn how to see, realize that everything connects to everything else." From this place of connected understanding, he became very prolific across multiple disciplines, making innovations in science, in anatomy, in biology, in engineering, and in art. Da Vinci and the other great masters have shown us that we no longer need to go through life with blinders on and look at things as separate. We can all learn to expand our vision and see the beauty of the connections that are all around us. And we can build bridges connecting our different disciplines and integrate our knowledge from a higher perspective.
Those very important moments where you read something or you look at it, a theory that's being propagated by the establishment. You have a choice to accept it as a truth and completely ignore what may be going on inside of you that may be saying something different. Or you might reflect on what you've learned, take what you think may be correct, and maybe see how you could add your view to it to transform it.
For the last 30 years, Nassim Haramein has been willing to ask questions and explore new ideas, and this journey has yielded ever further advances. Now, his work with Dr. Amir Valbaker has led to being able to extend his holographic mass solution to accurately predict the mass of the electron, the hydrogen Bohr atom, and all the elements of the periodic table that make up our physical reality with an unprecedented level of accuracy, one order of magnitude more precise than the standard approach is able to predict. All of these innovations are yet another step closer in helping us to usher in a new era of unified physics. We live in a time of great possibilities. We're all in this world together, and we are stronger together than we are apart. We have the opportunity to unify, to imagine the change we want to see in the world, to advance our collective evolution and advance our approach to science. We can imagine the world from a connected perspective, to see ways to create new ideas in science, health, business, and in living more connected lives. Many people around the world are experiencing a feeling and a knowingness that something incredible is happening, that there is a great shift in consciousness taking place, and that people are awakening to the idea that the disconnected worldview can transition to a more connected way of being. This supports some of the most advanced philosophical and spiritual concepts that we find throughout the ages, from masters that have come and told us that everything is connected and we are all one. They told us that there is this background energy, which is the force that creates stars, planets, and life. Science is showing us that there are infinite possibilities to explore in the vastness of the universe, and you have almost infinite possibilities to explore within yourself. We can create a new future for ourselves, and we can co-create together a positive future for humanity when we explore our connected universe.
I see
To shreds in a flash, collapse in on itself? Or will it slowly freeze to death? Scientists are imagining the unimaginable. And they're coming up with some wild ideas about how it's all going to end. This is the end of the universe. A battle is taking place in the farthest reaches of space. No one can see it, but scientists are certain that it's happening, and that the outcome is grim. The universe is going to end. It won't happen for billions of years, but there is no way out. Figuring out how it will end is the challenge of astrophysicists around the world. They're pointing high-tech equipment out toward the heavens to unlock the secret of our fate. The possibilities are frightening. In one scenario, gravity pulls the universe back into itself, similar to air being let out of an inflated balloon. The universe goes back to its original size. This is the Big Crunch.
That'd be the end of the universe, and a big fireball, as all the matter collapses onto itself. That'd be pretty dramatic.
Then there's the Big Chill. The universe expands until the nuclear furnaces that power all the stars burn out. The universe grows cold and dies.
A second possibility is actually kind of sad. The universe will continue to expand forever, and it will just grow into an increasingly cold and lonely place as the expansion removes our nearest neighbors from us, and we just end up a single isolated community of stars and galaxies.
Then again, there could be a much more spectacular end in which everything is ripped to shreds, down to the last atom. Think of it like a balloon that is filled with too much air. It pops.
It's much more dramatic than the Big Chill, and just as fateful as the Big Crunch. The universe continues to expand, but at an ever-quickening pace. And in fact, the pace is so great that even the space-time fabric cannot hold the universe together.
However the end comes, it will be a dramatic conclusion. To understand how it all could end, scientists turn to how it began. The mystery starts to be solved here, at the Mount Wilson Observatory overlooking Pasadena, California. In 1929, while looking through what was then the world's largest telescope, Edwin Hubble makes a strange discovery. The universe is expanding.
Hubble's discovery led to a whole new picture of the universe, that it was a dynamic environment and that it evolved. It changed in time, and that's different from pictures that people had of cosmology previous to that.
Before Hubble, scientists said that the universe was static and unchanging. Hubble's discovery that the universe is expanding meant it had a starting point, a beginning.
That brought the idea forward that, hey, what if we ran the film backwards in time and found the point at which that began?
The Big Bang. That fraction of a second when the universe and everything in it exploded into existence from a point smaller than an atom.
One common misconception about the Big Bang is that we can identify a point in space where the Big Bang occurred. But in fact, it's more appropriate to think of the Big Bang as a simultaneous creation everywhere of space, which is then continuing to expand to the present day.
Scientists theorize that at the moment of the Big Bang, the first small particles of matter called quarks were produced. They collided to form the building blocks of the universe. These floated in a thick fog of hot plasma for about 400,000 years. Gravity, also created at the Big Bang, drew the particles together, eventually creating the first stars and lighting up the cosmos.
The theory of the Big Bang is a very solid theory. What happened at the moment of the Big Bang is still something we're working on. We don't really understand.
If the universe has been expanding since the Big Bang, scientists must consider that it will stop expanding at some point. The question is, how? The most obvious answer involves gravity. What goes up must come down. Stars and galaxies and everything else might reverse direction. The universe would collapse in what some scientists call a big crunch.
Take the top and then see the other handle and just jerk them apart.
A model rocket offers clues to how the big crunch would work. The rocket is like the universe expanding into space out of the Big Bang. An initial bang allows the rocket to overcome the pull of gravity.
5, 4, 3, 2, 1.
Eventually, when the fuel is exhausted, the rocket coasts a few feet higher, stops, and is pulled back to Earth. This is what would happen with a big crunch. The entire universe is essentially pulled back to its launch pad.
The universe itself has its own momentum, its own energy. It's moving outward. But eventually, there's a point where possibly the universe will stop that moving outward, just like the rocket that we saw, and have to fall back in upon itself and collapse again under the force of its own gravity.
In this scenario, the universe could return to its original state just before the Big Bang, setting the stage for a perpetual seesaw of creation and destruction. The Big Crunch theory moved to a scientific back burner. Cosmologists figured out that there must be some form of energy that keeps the universe from collapsing. The existence of such a force leads to new theories about what the universe is made of and how it might end. And evidence about how this might play out is found in some of the most powerful and mysterious phenomena in the cosmos: black holes. Predicting how the universe will end involves some of the most advanced technology known to man. On a remote volcano on the island of Hawaii, astronomers are monitoring a battle in space that is shaping the fate of the universe. At an elevation of nearly 14,000 feet, the Keck telescopes bring astronomers from all over the world nearer to space for a clearer view of the cosmos. They come here because the telescopes work best far away from city lights and as high as possible above Earth's polluted air. Harsh conditions make it difficult to work here, but for scientists in pursuit of the great mysteries above, it's paradise.
So this is a remarkable location, but of course the air is very thin, it's extremely hard to work here, but these telescopes are amazingly powerful. But we're ambitious astronomers. We don't just stop looking at easy objects. We try hard to look at the very faintest objects so we can understand the extremities of the universe.
Here, astronomers like Richard Ellis are working on a problem that has been all-consuming for cosmologists since Edwin Hubble. They know the universe is expanding, but what they don't know is how fast. It will be difficult to predict exactly how the universe will end until they solve this mystery. The answers lie in the past.
Now, what I did the focus on was a V equals 12.
There it is, yeah. Okay, that's the dry star. We have
Get a better focus now. That was worth doing.
An astronomer like myself uses a ground-based telescope as a time machine. We're looking back in time to study distant galaxies, seen as they were a long, long time ago.
One of the distant galaxies that astronomers found revealed a powerful source of X-rays from something that they could not see. It was in the constellation Cygnus and emitted no light, but something was there. Whatever was emitting these X-rays had a mass about 7 times that of Earth's sun. There wasn't a name for it, so they called it a black hole. Black holes offer scientists an analogy to how the Big Crunch theory works. When certain stars run out of fuel, they collapse in on themselves into a smaller and far denser mass that attracts more and more matter, just like the Big Crunch. The gravitational pull is so powerful that anything that falls near a black hole will be forever trapped. Not even light can escape. It's a mind-boggling concept that something invisible is detectable and offers a view to our ultimate fate.
This black tarp represents space, and space is relatively flat. But when you put a massive object into space, it curves it. This is a penny, and notice how it comes into a really beautiful circular orbit. Basically, the black hole trapped it into an orbit around itself. And that orbit becomes very circular as it gets closer. And now the penny will eventually disappear, go inside the black hole.
Earth's sun warps space similarly to a black hole, only it's a cosmic wimp by comparison. The gravitational pull of our sun is much weaker. Earth and all its nearby planets are trapped by the sun's pull, but it's so mild that it just stays in orbit without being sucked into the sun. The mass of a black hole can be 1,000,000 times the mass of the sun, or more, causing a huge warp in the space around it that consumes everything that comes near.
That black hole wraps space around itself. And so if material falls near it, it falls inside and gets trapped forever.
Black holes exist in isolated areas throughout the cosmos. A black hole's gravitational pull is a scaled-down version of the force that could cause the universe to collapse. That force is dark matter, and dark matter is what scientists often call cosmic glue.
Hi, Matthew. So let's do some cosmology here. Dark matter attracts other objects via its gravitational attraction. It's a positive force.
There's another force that opposes gravity, and that is dark energy.
Dark energy, we don't really understand what it is, but it's a negative repulsing effect that pushes galaxies away from each other.
The whirlpool in Richard Ellis's demonstration represents the gravitational force of dark matter. The green dye coming out of the syringe shows how the stuff of the universe collapses under the force of dark matter.
The presence of dark matter acts as the focus for the gas in the universe, bringing structure together. This is how the Milky Way developed as the universe expanded. Little things merging into big things, the positive, constructive force of gravity. Now, if this was the only force in the universe would stop expanding at some point in the future, and eventually the universe would start collapsing. Gravity would eventually halt the expansion, bring it back together in a big crunch.
Yet the universe continues to expand and isn't showing any signs of collapsing. This suggests the opposing force of dark energy could be stronger than dark matter. But it will take scientific detective work to find out. They look to one of the most violent forces in the universe for clues.
We're studying exploding stars to try to understand if they can tell us the rate at which the universe is expanding.
These are explosions at the end of lives of stars, not unlike our sun. The fuel that these stars have in their centers is spent. The star collapses, the outer part expands, and the star becomes something called a white dwarf.
White dwarf stars sometimes have other stars orbiting nearby, a companion star. A massive explosion could happen if the companion star's debris falls onto the white dwarf, causing a spectacular fireworks display in the cosmos. Scientists consider exploding stars, or supernovae, like in these images captured by the Hubble telescope, to be reliable telltales of how fast the universe expands. Their brief and bright explosions allow scientists to track the universe's expansion and give them a way to measure its speed.
Essentially, they are white dwarf stars that become nuclear bombs. They explode with a certain brightness and a certain length of time. It takes a certain amount of time for that brightness to dissipate. They are essentially standard candles. Any one of these will look the same no matter where it is in the universe.
Astronomers measure the distance and speed of these exploding stars by measuring the amount of red light they emit. The faster the star moves away from us, the redder its light appears. The expansion rate of galaxies containing stars like supernovae can then be used to interpret how the rest of the universe is moving outward.
We know this because we can compare the velocities of galaxies with their distances.
These are the clues that lead astronomers to answer just how soon the universe will reverse direction and come back together in a big crunch. Or, this information might lead to an entirely different conclusion. Dr. Ellis is looking at clues at the Keck Observatory in Hawaii. While the telescope is on the top of a huge volcano, he's in a viewing room on another part of the island.
Hey, emission lines, Johan.
Oh, you see it?
In the red side, I think.
At the same time, Johan Richard is at the California Institute of Technology in Pasadena, California, evaluating the light from a distant galaxy that the Keck telescope captured in Hawaii. He's looking to see if any of the known elements coming from the galaxy are in the red spectrum and moving farther away.
We can interpret that as a velocity, as how much the galaxy is moving away from us. We can really interpret how the entire universe is behaving, is expanding.
Interpreting redshift is the cornerstone of the quest to pin down the fate of the universe. Clearer pictures of the universe that have only been possible in recent years have led cosmologists to conclude that the redshift of distant galaxies is greater than predicted. This is startling. Not only is the universe expanding, it's speeding up. Nothing in the observable cosmos could account for an accelerating universe, and yet the data seem irrefutable. This has to mean that an invisible force is working against gravity. Cosmologists have come up with a name: dark energy.
So when the universe was young, gravity was the most dominant force. And so what we see here is galaxies as particles on the surface of the water are bound together by gravity. And at a point about 7 billion years ago, dark energy and gravity are pretty well in balance. But the universe continues to expand, the density goes down, and so dark energy starts to take over. And lo and behold, the universe starts to accelerate. So dark energy is now the dominant property of space.
So the universe started out with a certain amount of energy, and we know we're trying to understand how much energy there is, and we know the universe is expanding as it moves outward with time. We also know now that the universe's expansion is accelerating, and we don't know, is that acceleration going to slow down or not? We're still trying to understand that. So in understanding what's going to happen to the fate of the universe, we have to know how much energy is there, how much matter is there.
The history of the universe is really a battle between dark matter and dark energy. These two forces are in opposition, and so both the history of the universe and its ultimate fate is really the competition between these two forces.
The Big Crunch theory was a result of scientists interpreting that dark matter is the dominant force, but astronomers now suspect that dark energy might be much stronger. If so, the end could be dramatic and violent.
It pulls apart solar systems, it pulls apart stars, and eventually it grows so strong that it pulls apart matter itself, breaks bonds, pulls apart atoms, and reduces everything to fundamental particles, and that's the end of the universe.
The battle between dark matter, the force that holds the universe together, and dark energy, the force seeking to tear it apart, has set the universe on a path of destruction. If dark matter is the victor, the universe might collapse. If dark energy rules the cosmos, it could rip to shreds.
The expansion grows so strong that it tears up the entire universe.
It'll be a strange twist of fate. Dark energy, the force that propelled matter to form a magnificent universe, continues to push it outward and drives it to its demise. To find out if dark energy is in fact winning the battle, scientists will first need to know how fast the universe is actually expanding.
The most remarkable feature of the universe is that it's expanding. Every galaxy is moving away from every other galaxy. When you look out into the night sky, you see distant stars, galaxies, clusters of galaxies they observe with telescopes, and they're all moving away from us. We can illustrate that with this balloon. As we expand it, we see that every dot drawn on this black balloon, like the night sky, is moving away from every other dot. But there's something else that we know about the universe, something else that we know about the expansion. That is that the expansion is getting faster. The universe is accelerating. The size of the universe is getting bigger at a faster and faster rate. And we don't know exactly how fast it's accelerating, but if it's accelerating fast enough, then something really dramatic could happen. The universe could end up tearing itself apart in a big rip.
This is perfect. This is great that you rigged this up. So this is a giant version of the demo that I do in class.
Dr. Robert Caldwell attempts an earthbound experiment to show how dark energy affects the acceleration of the universe. He uses a paintball gun mounted on a truck.
Yeah, and basically, I mean, we could adjust the angle in any way that you want it. What do you think about this?
I think down at the ground,
a little bit more
is the best, so we can mark each time the gun fires. That'll be good.
Let's try that.
He sends the truck coasting down an incline. Earth's gravity pulls the vehicle downhill, which is similar to how dark energy propels the universe outward, causing it to expand. Gravity pulls the truck forward at an increasing speed. The gun fires paint at the ground at regular 1-second intervals. Caldwell measures the distance between the paint dots to calculate just how fast the truck was accelerating. He'll use the data from this experiment to see how gravity's force compares to dark energy's force in the cosmos.
We started thinking about the Big Rip when it was discovered that the expansion of the universe was accelerating. The degree of acceleration is not known, and it's the subject of a lot of effort by astronomers today to try and figure out exactly how fast the expansion is growing. What is the past evolution of the universe in detail, and if we can glean from that, what is the future evolution of the universe? It's not known exactly how fast it's accelerating. There's some evidence that the acceleration is beyond a certain threshold, and beyond that threshold, there's a runaway effect that could take place, and it would rip apart the universe.
Good luck. Fantastic. I think we've got some good data.
Excellent. How do we measure this?
Great. Give you that end.
All right.
I'll take this.
5 feet, 8.5 inches.
The point of the paintball experiment is to find parallels between the truck propelled by the invisible force of gravity and the accelerating universe.
I'm glad we got the long tape measured because it's really growing pretty fast, the interval.
Within a few measurements, the distance between the paint spots increases by nearly 7 times. If the truck were in space, at this rate, it would travel faster than 100 miles per hour within a minute, and over 1,000 miles per hour within 10 minutes.
They're getting big now.
Here we got 42.5 feet.
42, all right, 0.5.
The question for Robert Caldwell is whether the same kind of expansion and acceleration are happening on a cosmic scale.
What's the capsule made of? Is it plastic or some kind of
gelatin?
Okay.
It's all biodegradable.
So
you could actually eat them if you wanted to.
This right here is the data that I took with Eric. The cumulative distance traveled by the car as a function of time, and that's beautiful. It's this nice parabolic shape. That's exactly what you expect for an accelerating body. Now over here I've got another calculation going on where I'm working out the acceleration of the universe.
Robert Caldwell's calculation shows that forces on Earth are similar to forces in space. This demonstration, then, gives a sense of the dramatic rate of expansion that appears to be happening in the cosmos.
By eye, it might be difficult to appreciate how good a fit it is, but I can tell you that the weight of the statistics indicates that an accelerating universe is a very good fit to this data.
If, like the truck, the universe is continually accelerating, then billions of years from now, the universe might tear itself apart.
All the distant stars and galaxies will be pulled away from each other. They'll be pulled away from us. But moreover, we won't have time to grow cold and lonely. It'll actually be pretty exciting and dramatic and violent. Stars are ripped apart, planets are ripped apart, and even atoms are torn apart before the universe ends. It wouldn't happen for at least 50 billion years, but still it's an interesting fate for the universe.
What would atoms ripping apart look like? Things like coffee cups are solid. Atoms join together to create something that will hold a cappuccino without leaking a single drop. Zoom in through the cup, like sailing through the cosmos, past the molecules and into the atoms. The solid cup is nothing more than a fabric of atomic particles that formed a bond to become matter. If these particles were to move apart, the bonds that hold this cup together stop working. The atoms no longer support molecules. The connections between the minuscule particles dissolve. Matter in the form of this cup ceases to exist. It disintegrates, gone from existence. This is the dramatic end that Robert Caldwell foresees for the universe.
What you would see if you were standing on Earth or standing on some other planet that happened to still be around at that time, you would see something that looks like a wall of darkness approaching you. And as the wall of darkness approaches, stars would go out, galaxies would go out, and then eventually that wall of darkness would surround the planet. And then pretty soon, atoms themselves are torn apart, and that's it. Just the wall of darkness shrinks down to a point, and that's the end of the universe.
According to Robert Caldwell, that moment is still billions of years off, leaving plenty of time to refine the research.
In a way, this is like a detective story. We're trying to figure out what is the culprit, or who is the culprit responsible for the cosmic acceleration. We think we know its name. We call it dark energy, but we don't know the modus operandi. We don't know exactly how it works. And what's needed is more information about the physics behind the dark energy. We want to know exactly what it does and exactly what it's made out of. And in answering those questions, we'll be able to figure out exactly what is the fate of the universe.
The Big Rip is one theory. Cruising just above Earth's atmosphere and peering deep into space, the Hubble telescope provides scientists with clues to a less violent, but equally unavoidable, end of the universe. Scientists now say the universe is expanding, and that depending on how fast it is accelerating, it might end in a big rip where everything tears apart. It's also possible that it will continue to expand, but at a slower rate. The universe wouldn't rip apart, but would become dark, cold, and lifeless.
If dark energy turns out to be constant, a constant property of space, and continues at the same rate that it is now, the universe will keep expanding forever, and it will be a very sad state. I think in the end, it just chills out. Everything cools down.
Evidence for the Big Chill and all of the theories for the end of the universe, in part, come from the Hubble Space Telescope. It has been orbiting Earth since 1990 and has an unobstructed view of the cosmos. The extraordinary images it beams back to Earth are amazing in their clarity and detail. And because of Hubble, scientists can make better predictions about how the universe will end.
So here is an example of a very deep field that was taken by the Hubble Space Telescope, which literally you point the space telescope at a single region in space. And if you looked at this from a typical ground-based image before Hubble was launched, first of all, it's literally almost size of a postage stamp. And so suddenly, the first Hubble Deep Field that was ever taken had 4,000 galaxies that looked just like the galaxies here, that were never visible before from the ground. A tremendous power. Each of these smudges in their own right is another galaxy. Each one of these galaxies contains about 100 billion stars.
Hubble sees more than just stars and galaxies. It just might be onto one of the key ingredients of space. An invisible ingredient that could put the brakes on dark energy's effect and cause a big chill. That's dark matter. Scientists talk about dark matter as the substance that holds the universe together and could prevent a big rip. Evidence that dark matter exists is seen in some of Hubble's images of nearby galaxies. It sometimes appears as though other galaxies surround them. The other galaxies are not really there at all. Rather, they are reflections of more distant galaxies coming from behind. Astronomers suspect this optical illusion is dark matter causing a weird distortion of light called gravitational lensing. The light from the more distant galaxies is literally bent by the curvature of space caused by stars and dark matter in its path. The more dark matter there is between Earth and the distant galaxy, the more the light will be bent and the greater the force to cause a big chill.
The gravitational lensing is a tremendous tool for the astronomer because we can measure the distortion in background galaxies and use it to trace the distribution of dark matter on various scales. We're looking at a distribution of idealized galaxies here on the sky, and the light from these distant galaxies is passing through clumps of dark matter. What you look at is not really what's happening. It's a bit like wearing spectacles and not knowing that you're wearing them.
And if you can tell how much that bending is occurring, you can map the dark matter, and you can also see, well, if there's dark matter there, is the universe around that dark matter behaving the way it should given the gravity or not? If it's slightly gravitating less, then dark energy might be changing in those places.
Identifying which energy force dominates, dark matter or dark energy, will give scientists more confidence about whether a big chill or a big rip will be our fate. The best evidence shows dark energy as the driving force, but by how much? Solving this mystery depends on astronomers finding ways to measure how fast the universe is moving. On Earth, it's simple to determine how fast something moves. An airplane, for example, is relatively close. We can look at it and calculate its speed by estimating the distance it travels and timing how long it takes to get from one point to another. But a star's light can travel for millions or billions of years before it can be seen on Earth. By the time its light gets here, the star will be long gone, and it's too far away to gauge its speed or distance traveled with any certainty. The universe is expanding, only scientists cannot give precise answers about how fast. The mystery moves closer to being solved by imaging the cosmos with greater precision. Clearer images from space make it easier to estimate the rate of expansion.
If the universe continues to expand with time, then ultimately all of the energy sources, the nuclear furnaces in stars, would run out and die, and the universe would actually get very cold, and there'd be something called a big chill.
In the big chill scenario, Earth could become a lonely, cold planet as the universe expands. Distances between stars grow so vast that they nearly disappear from view. Over time, they burn out, and eventually the entire universe ends in a frozen state. This sphere demonstrates the principles behind a big chill. The marbles coming out of the sphere are like stars that were formed following the Big Bang. Dark energy propels the stars outward. Dark matter slows them down. In a big chill, the expansion would continue, but the nuclear fuel that causes the stars to burn will eventually run out. From Earth's perspective, the first thing to go would be sunlight. The sun dims as it exhausts its last bits of nuclear fuel. Earth would freeze and become lifeless. And billions of years after humans are gone, the cosmos expands out of view. A few newer stars might remain, but most would have long moved away. The furnace powering the universe burns out. The darkened universe continues to expand, a frozen and lifeless remnant of its once vibrant existence.
Eventually, if this keeps going, if nothing changes in the composition of this energy density, the universe will continue to expand forever. It's going to get colder and colder, and eventually even our neighboring galaxies will be receding from us so fast that we won't be able to see them. So the universe is going to get cold and dark, and it will be a very lonely place.
Astronomers have much to learn about the influence of dark energy and dark matter, and much of the newest information is coming from this probe in deep space. It's sending back information that's helping scientists to interpret the history and the fate of the universe. The night sky, by all appearance, is a quiet and peaceful place, but in reality, there are forces that are driving it to an end. Big science moves astronomers closer to deciphering the universe's great mysteries, including its ultimate fate. The solution to the universe's riddle may well be hidden in this multicolored image. What's incredible is that it's a map of the early universe from the moment it was conceived. And even more fantastic, it reveals a great story that helps cosmologists predict how how it will end. The machine that captured this is called WMAP, a NASA satellite that's working around the clock to chart the cosmos.
What we're looking at here is the edge of the visible universe. It's the light that WMAP measured, it's the remnant heat from the Big Bang, and this is literally the oldest light in the universe that we can see. This fossil relic from the early universe tells us a great deal about what the composition of matter was like, what the expansion rate was like, and really what the conditions were at the birth of our universe.
WMAP is one of the great astronomical breakthroughs of the 21st century. Nothing before could give us such a clear image of the energy left over from the Big Bang, energy that scientists call the cosmic microwave background. WMAP is measuring temperature differences in the cosmic microwave background, which may finally make it possible to predict which force will dominate the universe and how that force will bring the cosmos to its end.
The blue spots are regions in the microwave light that was produced by the Big Bang that are slightly colder than the average temperature, and the red spots are regions that are slightly hotter than the average.
Temperature differences revealed by WMAP tell scientists about the nature of the matter and energy that is contained within the universe. They're able to analyze the light patterns and find clues not only about the substance, but also the fate of the universe.
We only capture a tiny part of the electromagnetic spectrum with our eyes, and we have to go to much longer wavelengths. The same wavelengths that are used to heat water in a microwave oven are what we're measuring here with WMAP.
WMAP is so precise that it can detect differences in temperatures as small as 1/1000th of a degree. This sensitivity helps scientists to calculate the ratio of dark matter to dark energy, forces that will determine how the universe ends.
We assembled all those difference measurements and make a map of what the variations look like. And by turning up the contrast, we can basically subtract off this uniform glow from the Big Bang and look for variation.
It doesn't look like much until Gary Hinshaw adjusts the contrast. Then the WMAP image comes to life. Looking at WMAP imagery is in essence taking a journey back through space and time so that we might get some new ideas on the fate of the universe. Pulling away from the probe and following the path of the light it is collecting, we pass Mars, Jupiter, and Saturn, whose reflected light takes over an hour to reach Earth. Then, leaving the Milky Way, we pass Andromeda, the next nearest galaxy, whose light takes 2.3 million years to reach us, which means we have traveled 2.3 million years back in time. And finally, we arrive back 13 billion years ago, at the beginning of visible light. Before that, superheated hydrogen gas is everywhere. WMAP can see this far back in history. It's confirming important facts about the universe and what's driving it to its demise. The final act for the universe becomes more easily predicted thanks to WMAP. Its information, combined with the work of astronomers, has led to some astounding discoveries concerning a rapidly expanding universe. Rapid expansion supports the dark energy theory and the possibility of a big chill or big rip.
We now know from all the data we've had in the last 10 years that there's, by a factor of 2 to 1, more dark energy than dark matter. So dark energy is the dominant constituent of energy in the universe.
The evidence seems clear. Dark energy is taking over and is leading astronomers into new thoughts about the beginning and the end of the universe.
Before the discovery of dark energy, things were a lot simpler. If we could determine the amount of matter in the universe, then we could say something about its ultimate destiny.
Those simple days are gone, but the proof is adding up and supports the idea that the universe will continue to expand. But will it do so to oblivion?
We've made huge strides over the last century in learning something about the evolution of the universe and its expansion. But we've now raised more questions in some sense than we've been able to answer. And so I think the next decade is going to be even more exciting.
Astronomers have tons and tons of challenges that have been thrown our way by theorists, and we are rapidly trying to figure out how to answer all of these questions. And I think that's the exciting future, because if you can go out and really observe something, you're testing it. And that's what science is all about.
The battle between dark matter and dark energy is expected to go on for billions of years, and humans will be long gone from Earth when the final outcome occurs. But no pursuit has been more significant to science than understanding how the universe arrived, how it works, and how it will end.
It's a never-ending quest. It's driving astronomy. What are the answers to these profound questions? The constituents of the universe, the nature of dark matter, and perhaps the biggest mystery of all, what is the ultimate fate of the universe?
you.